Good morning, everyone. Maybe on the comment, I think making it human again is because the data naturally comes from humans, and then you put it back into the method. So I will talk about Explainable AI. It's something we use in QuantumBlack, and maybe I will give a brief introduction in like what we do, continue with what is Explainable AI, XAI, and then move to two methods that we use internally as well. Give a bit of a flavor what it looks like when you use it in practice, and then we can finish up with some questions. So QuantumBlack is fairly young. I think we celebrated 10 years, but it really took off only in the last few years. We got acquired by McKinsey, a strategic consultancy, and we do data science consulting. We try to use state-of-the-art methods to empower companies, organizations to achieve their missions better or grow their business. I'm Pilgerstorfer. I'm a data scientist, as introduced. I've worked in a couple of industries already. I have used XAI on client projects as well, and it's, I think, increasingly more demand from the clients that they want to have something like this. Maybe they cannot name it, but there's a growing demand for explainable AI. Let's start with why do we want to have explanations? And we think in terms of those four buckets that you see here. The first one is to build trust. Imagine that you have a tool that you give to a doctor, and you get the probability of a patient getting a disease. In itself, that might be very powerful, but there's still a human component in the sense that whoever's operating the tool also needs to trust it, otherwise there's no adoption. And if you maybe just put, these are the 5 variables that guided the black box decision, often that is enough to build enough trust for the doctor to really use it reliably and make use of the good prediction that you get out of the machine learning model. Second point is legal requirements. So for example, in insurance and financial services, depending on the country, but you have a requirement that you need to explain your decisions. So if I use a tool, a predictive model to try to predict your risk score for car insurance, the customer can demand an explanation for why have I been put into this bucket. It's still a black box model. You can't you have a random forest with 1,000 trees. You can't explain it in detail, but you can explain it on a higher level. That is also maybe better to ingest from a human perspective. So you can use Explainable AI to meet the legal requirement for those industries and those use cases. The third part is concerning ethics in AI. If you have, the technical term is a protected feature, which might be the ethnic background, might be gender, might be whatever is the appropriate feature in the use case, that you don't want to discriminate with respect to that feature. And if you get an explanation where you see that the decision was made because the patient is female, you can look deeper and figure out, okay, is this because our method is biased in itself? Does it learn something from the data that uncovers a bias that is present in the data as well? And is this something that we should mitigate? Is there like reasonable scope? We have I think it's called tutorial in the afternoon on fairness in AI. This is headed by Charles, and so if you want to know more about this aspect, he's not going to talk too much about explainable AI, but about fairness. Please join that session. And the last part is you might have a predictive model. Coming back to the doctor, you can predict certain disease very well, maybe cancer. With explainable AI, in some cases you can actually you can figure out what is the important part here, and it will not give you the causal effect, but it might guide you towards something that you can then explore further. So you could say, okay, actually some tissue part in the scan is important. So maybe actually when you do the manual check, that's something that you can focus on as well. And maybe you will find a better way to do it manually as well. We have discussed why, and I hope I could convince you that there's a lot of cases where we do want to have an explanation for a model. What makes a model, or like what makes an explanation good? We have the abbreviation CLIM. It's if you try to explain individual parts, so for example, patient journeys, you have different patients, you try to explain why does the model think that the individual features matter or do not matter. And aggregating those individual points should make a coherent picture. So explaining locally should have a global, should give you a global understanding. The second part is when you do look locally, it should reflect the model. So at least if you have a simple model that explains the decision for similar patients, it should be fairly accurate. So it should reflect the model performance. The third point, I like that one because it's interpretable. So it's like we want actually the interpretable model to be interpretable as well. Coming back to a point raised before, like you need a human to understand this as well. So if you have a random forest with 200 features, if you have a convolutional neural network with, I don't know, 1 megapixel images, you're not going to be very happy with 1 million points where maybe some of them are important. So you need some sense of like really reduce the dimension as well, because as a human you just don't have the capability to absorb that very high dimensional problem. And so this is when you do look locally, you can probably reduce the important features to a handful. And then that's something that you can ingest. And I mean, you can do other aggregation mechanisms, manual or maybe automatic as well. But in the end, you need something, an explanation that is like absorbable. And the fourth point, personally, I don't think it's good to have, but I think you can relax it sometimes. It's model agnostic. So if you have a model that explains something, it should not depend what model you actually trained on. So your prediction, does it come from a neural network? Does it come from a random forest, a gradient booster, or whatever method you have, linear regression? But then you probably don't want to have an explanation. And you can relax it. We will come to this in a tiny bit. Conceptually, where does like the explanation come in? So we have the data. Oh, we really want to have data. We build a model, and then we get a prediction. So ignoring the XAI and explanation part, this is like the the typical workflow that you would have in a predictive case. So then you would add this, and it is a post hoc explanation, right? It's on top of the predictive model, which you just add there. It ingests the data. It also uses the model because it tries to explain it, and it will give you an explanation, maybe globally, like a feature importance type, or actually locally, so then very specific to the prediction for an individual data point. And so there's other methods as well, and I mean, like, linear regression is one example where actually the predictive model, even though maybe the prediction is not very good, could be, like, is the same as the explanatory model. If you have very high-powered predictive models, it's getting very difficult, and you will have a trade-off between performance and explainability. And with a post-hoc analysis, you kind of break it, but it's, I think, a big stream of literature is dealing with this type of explainable AI. Let's go to methods. So there's been a lot of development in the last few years, and it's still continuing. I think every big conference, there's new papers on maybe fine-tuning existing methods, figuring out that, oh, this method that we had last time wasn't consistent, so actually I propose a correction. And so it's a very quickly developing field still, which is exciting, and I think this, I hope I convinced you, a lot of demand for it as well. At QuantumBlack, we use two methods mostly. The first one is line. So roughly speaking, you build a linear model locally for specific points. I will go into this a bit more into detail on the next slide. And SHAP, which is, I would say, the better version of line, but at least I prefer to use this one. It has a bit better, like, theoretical guarantees. And there's adaptations to, like, neural networks. For example, for convolutional neural networks, you're not dealing with tabular data, you're dealing with an image. So also, like, your explanation should reflect that you have filters, you don't have, like, weights in that sense, and that will, like, affect the way you should visualize the importances. And here I'm coming back to the model agnostic part. So this is just, it's not exhaustive, but so Lime and the kernel SHAP, which is like the traditional SHAP, they're model agnostic in the sense that they can take any predictive model in. But they do have quite high computational cost if you make it specific. So for example, with tree SHAP and deep SHAP, it's specific to this type of model, but you will get much better computational complexities that actually make it usable in some cases. And with regard to software, I think there's a tutorial later on in R. We mostly use Python. The GitHub pages I posted here are, I think, from the authors of the papers. They're in Python. There's actually, I think both of them are available on pip. There's several adaptations in R as well. And in the afternoon tutorial, you'll probably hear more about this. Let's have a slightly deeper look into Lime. We have, I hope you can see it. We basically try to build an explanation locally, right? So that's in the name. Locally interpretable model agnostic explanation. So XAI X is our explanation. And what is it? We try to, don't focus on the mathematics too much maybe, but we try to fit locally our explanation to the predictive model, but we do want to penalize complexity. And this is the part with, we want a simpler explanation. So in most cases, this could be less so, where we just want 5 features, or maybe more, depending on the use case. But we want something simple. It might be a decision tree as well, but one decision tree, not an ensemble of 5,000. And in the end, what it boils down to is you really fit the model around the neighborhood of the point that you're interested in. So this is, you can generate data. You generate the labels with your predictive model. And this is really, you're explaining the prediction. You're not necessarily explaining the underlying phenomena. And then you build linear classification. You build some simple model that will help you explain this local neighborhood. As mentioned before, SHAP. So my favorite. You have some properties that are nice. So the first one is you want to be locally accurate. So with Lime, maybe it's based on sampling. It will still converge, which is good. But there's very few guarantees. With SHAP, which is based on a SHapley value, me coming from econometrics and having done a lot of game theory, this is very nice. With locally, you are accurate. So locally, you can actually decompose a prediction. I get a probability of 80%. I can figure out which features contribute to this 80%. Missingness is another property here, which is basically if it doesn't exist, or like if the feature is missing in this particular case, we assign 0 value to it. And consistency is basically if a model assigns more value to a feature, you should also have a higher attribute for that feature in terms of explanation. But in the end, and we come now to the game theory part, is those properties you can frame as a cooperative game. There's this unique solution, which is the SHapley value, and it will look like this. So we have a unique, you have an additive model, and you can actually calculate all those values exactly. You can also sample them. And just intuitively, what is the SHapley value is like the contribution of a feature if it gets added to a random subset of the other features. And this will give you like the feature contribution of that value. And you can do this for each point in your data set. Let's continue with some visualizations. So first one is a dummy data set. So this is the UCI adult data set, which is more like to show you how those things look visually. Because I understand that talking about feature importance and explanation is difficult. If you see it, I think you get a much better sense. So we will look at this first, and then I have a use case very similar to a project that we have done in QuantumBlack in the insurance space. What do we have here? We have the adult dataset, which is a dataset where the goal is to classify whether a person is high income, low income, given a threshold of $50,000 per year. And you have several socioeconomic features, and the data set, it's 30,000 points training and 16 for test. And since this is real world, I think it's based on census data. So this will incorporate biases that exist in society today. And again, come to the workshop in the afternoon. We're not going to try to uncover those here, but this is an issue that you have with those type of data, right? First example, Lime. What do we have? We have so on the left side we have the probabilities. So this is for a specific person. For a specific person, we get 19% probability of low income, 81% probability of high income. It's binary, so this is not a surprise that it sums up to 1. On the right side, we actually have the values of some of the features. So we have that person got $8,000 in capital gains. We have the person marital status is married and didn't have any capital loss in the year of observation. And they worked 50 hours per week, and he or she, I don't think it says here, is 41 years old. And now we can combine this. Now the explanation comes in, which is the middle part. So anything left of the line is the contribution towards 0, which is the low income bucket. And on the right side, it's the contribution towards a prediction of high income. And we see having capital gains of $7,300 is a very strong indicator that the person earns more than $50,000 per year. Same for being married. And then the others are maybe not as important. For SHAP, we can also get something similar. Or maybe the visualization actually comes from the package. So this is nothing we have internally. This is readily available with Lime. And with SHAP, it's the same. So this visualization comes from the package as well. In Python, I'm not familiar with the R. You can, though, get the values just in raw format, and you can ingest and digest it whatever way you want. So here we look at a typical example. So we have a person which has a probability of high income of 22%, which is roughly the average in the data set. And we can see in those visualizations, so on the left side, this is features that contribute to a higher score, and then on the right side, features that push it down, the probability. And we can see, so the two dominating factors here is the marital status, being married, so the two, this is more legend over there, 2 indicating married, and the age is 21. The age contributes negatively in this case, because probably with 21, maybe you don't have enough experience. And we actually have education as well, which is also codified. I think 11 is around high school. But we see those forces that push and pull in different directions. And it's a nonlinear model, right? So depending on the feature values, those things might change. We can look at a case with high probability, and we see again, this is a person with high capital gains, which is something that actually Lime told us already as well. So they do show similar things, not all the time, but in the big factors, they do capture similarly. And then we can have a person with a very low score of being a high earner. We actually see the marital status in this case is married but with absent spouse. And we see the age is contributing positively, which is probably a factor of experience in this case, or a proxy of experience. At the same time, the person doesn't work as much with 32 hours, so pushing down the probability again. And so this can give you like a sense of like what is important. Actually, in my last project, which was looking at patient journeys, we used explanations to figure out whether the model performs well. So it's like, does it capture certain aspects in the patient journey that we want to use? And so it actually informed us during the model building as well. And so this was 3 patients. If we stack all of the patients in the data set together, we can, the package can sort it as well and kind of cluster them. And then we will get, on the left side, for example, people, and we've seen this, where with non-zero capital gains and positive capital gains, and then it really doesn't matter what else you have. And this is, similar image as we have seen with the individual points in Lime and in SHAP. And we can look at a few others, but I think it's not too interesting. You can see like a through with young, non-married, few years in education. Also a case that we have seen before with basically you're young, you might be actually still like a student, and so your ability to earn 50,000 a year is maybe not as high. Let's continue to the final part, which is a use case. So this is in insurance. On the left side, we want to determine the risk score. On the left side, we have good weather conditions. Maybe the driver is familiar with the road, so we would attach a low probability of accidents. On the right side, adverse weather conditions, inexperienced driver maybe. So we can attach different values here. And the way we approach this, so we start out with like 1,500 features. We reduce it with some feature selection. I think it was lasso or elastic net, down to something that a random forest can handle better. And then we use this to build a model to predict the risk score. However, a big focus was also on the explanation. And that was us using Lime and SHAP. And maybe we've gone through a few examples. I will show you how this was used in the final output that we delivered in this case. Or at least a dummy plot, very similar to what we delivered. We have the prediction. This particular person is 6.8 risk score. We have some supporting information, which is your last journeys, maybe some characteristics about acceleration and those things. But then the middle part is an explanation of why the person gets the risk score that they do get. And this is, so we did have like 100 features, so you bundle them together. This can be a manual process, or you can be a bit smarter. And then you try to see whether your contribution in those buckets, so in the cornering bucket, for example, whether the contribution is positive or negative. And then you would end up with your corner driving style is increasing your risk of an accident. So maybe we can encourage the drivers to improve their score. And then we have a button at the bottom which says, okay, so you're well below target. The target is basically you don't have a positive or negative contribution. And if you do want to improve your driving, maybe look at this, and then there might be links to external resources. I think that's it.